here we have a real sequence that's bounded and also given the limit of a sub 2n plus 2 times an altogether approaching 0. And we want to show the limit of the original sequence is also 0. So there is not too much information I can extract from the given condition. How do I know the limit of an is equal to 0 then? Right? In this case, we're going to use the strategy of lim_inf and lim_sup. So first of all, we'll recall the meaning of lim_inf. Right? So one of the definitions is that this is the defined to be infimum of the set E, where E is equal to the set of all the limit points of an. Right? Okay. So what does that mean? So a sequence may or may not converge. Right? If it's not convergent, if it has somehow a subsequence that's convergent to a limit point, we call that a limit point of that subsequence. We have several convergent subsequences. We put all that limit points into this set, call it set E. There might be finitely many elements or infinitely many elements. Right? All are possible. And we take its infimum, we call it lim_inf. And likewise, lim_sup is the supremum of this set. Right? For example, this sequence, obviously divergent, oscillating between 1 and -1. But we know it has two subsequences. One subsequence converges to 1, the other converges to -1. So in that case, the E is equal to this. All right? In this case, the lim_inf is just -1. Lim_sup is 1. Also works for infinitely many limit points. Also the case. Right? And the best part is that, in fact, I can prove it, not in this video, maybe in a future video. But that's a standard result that says, not only that, actually the limit that also sits in this set. Supremum also sits in this set. It can be proven. Right? Normally, that's not the case. For example, open set 0, 1, open interval. The infimum is 0, but 0 does not live in this set. Right? But in the lim_inf and lim_sup, it can be proven that they actually lives in that set. Right? In a future video. So why am I going to use this? All right, so as long as I can show that lim_inf is equal to the lim_sup, then I can immediately show that the limit of original sequence exists. Why? Because if this is equal to that, all right, which means infimum of E equal to supremum of E, what does that mean? That means the set E only has one element, right? Otherwise it cannot be true. So only one element in set E, which means there's only one limit point. So which means if a subsequence is convergent, then you take all the convergent subsequences, take them all in there. They all converge to the same limit point. So which means the original sequence has to be convergent. Otherwise it cannot be true. So can I actually show this equation is true for this an. Okay? So first of all, let me just prove another standard result. So I say as long as the original sequence is convergent, then you take any subsequence of an. I can show that the limit also exists, also equal to a. Okay, let's prove that if the sequence is convergent, then any of its subsequence also convergent to the same limit. First of all, let's recall the meaning of subsequence. Right? The original sequence. A6, A7. All right. Now I take any subsequence. Perhaps this, perhaps that, perhaps. The rule is that you cannot go back. You cannot say first one, second one, third one. You cannot go back. It has to go forward. First, second, third, which means this is my AK1. This is my AK2. This is my AK3. Right? So the subscript of my subsequence is K1, K2, K3. And the pattern is that clearly K1 is just the 2, right, original. 2 is bigger than 1. K2 is nothing but original 4. 4 is bigger than this 2, right? K3 is 7, bigger than 3. Right? So what I'm trying to say is that in general, Kn is bigger than n. Kn bigger than n, right? This is clear. Right, so what I'm trying to say is that the subscript of our subsequence runs faster than the subscript of the original sequence. Right? So to prove this result, use the original definition. Given any epsilon greater than 0, there's capital N as long as little n is bigger than capital N. We always have the absolute value of an minus a is less than epsilon, because that's given, right? The original definition. Now, since Kn is bigger than n, right, therefore I can say that as long as I let little n bigger than this capital N, epsilon fixed, capital N fixed. Now I let little n to be bigger than this capital N. This doable, right? Absolutely doable. Also knowing this, Kn is bigger. So which means the absolute value of, so again, translating into English, this is telling us as long as this little number on the right hand side, bottom corner of A is big enough, then this absolute value can be small enough. So which means, do we have the little number on the right bottom corner of A that's big enough? I use K sub n as my little number on this right hand bottom side corner. Is it big enough? Yes, it's bigger than n. N is bigger than capital N. Yes, it's bigger than capital N. It says, as long as this little number is bigger than capital N, then this can be small enough. Which means, yes, as long as this little number is bigger than capital N, then this distance can be small enough, right? So that's the very definition of limit of the subsequence, right? As n approaches infinity equal to a, the very definition, right? As little n is big enough, bigger than this capital N, this can be small enough. Okay, now we can just move on to our main dish, that is this. So how can I take advantage of Lim's soup, for example? If I let Lim soup, I call it A, because it says the sequence is bounded. Right, bounded. Remember, Lim soup is the supremum of all the limit points. Right, all the limit points must be bounded as well. So supremum has to be a finite number as well. So A is some constant. In that case, what can we say about this? Okay. So that's telling me that there must be some subsequence of a_n whose limit happens to be a. Like I said, I'll prove it in a future video, but that's a standard result, which says the Lim soup also lives in that set that contains all the limit points, which means there has to be a subsequence whose limit happens to be a as well. Right? Now, what can we learn from that? Okay, I can replace this n with kn and still achieve the same result. Why? Because if I let bn equal to a sub 2n plus 2 a sub n, right? Call it bn, a whole entity as a sequence, given to be limit, given to be 0. So what does that tell us? That tells us, like I said, I've just proved that result, right? If the sequence is convergent, then any of its subsequence has to also converge to the same limit. So if I replace n with kn, meaning taking its subsequence, right, b sub kn is equal to a sub 2 times k sub n plus 2 times a sub k sub n also approaches 0. Right? So I can also tell that, because I already said that there is a subsequence approaching a. Right? So a sub kn, this is the same thing, right? A sub kn. 2 times that, so this is approaching 2a. Right? So which means this is approaching what? Negative 2a. Right? 2k approaching negative 2a. Now, this is also a subsequence. It's just different subscript. Used to be little n, now it's 2 times kn. It's nothing but a subsequence. I don't know what exactly that is, but there's a subsequence. So a subsequence approaching to some limit. And this is the supremum of all the limit points. So which means this limit point is no larger than that supremum. Right, by definition, supremum of all the limit points. So 3a bigger than 0. A is bigger than or equal to 0. Right? And again, now I'm going to replace this n with 2n, meaning also taking its subsequence, just an even sequence, even terms, right? No problem. Same result, still approaching 0. b sub 2n, a2n becomes a4n plus 2 times a, n becomes 2n. The same result, right? What do I know next? I've just found out that a sub 2 times kn is approaching this, which means as long as I can replace this n with kn, then I immediately have b sub 2 times k sub n, that's a sub 4 times k sub n plus 2 times a sub 2 times k sub n approaching 0. Then I can take advantage of this result. 2 times kn approaching negative 2a. This time times 2, approaching negative 4a, which tells me this is approaching what? Whole thing approaching 0, so must approach 4a, right? I don't know what that is, but that's just a subsequence, right? This is just some random subscript. Like I said, again, some subsequence, that's its limit point. So limit point is no larger than that lim sup, which is the supremum of all the limit points. So again, 4a no larger than a. So 3a no larger than 0. So a no larger than 0. Right? Previously I said I reached a is bigger than or equal to 0. Now a is less than or equal to 0. So right, a must be equal to 0. Lim sup. And of course, next I'll do the lim inf, next step, following the same procedure. The only difference is that perhaps I changed the direction of the inequality, because next time I use lim inf. So any subsequence limit point is bigger than or equal to that lim inf. Right? So maybe next time our next step would be a is less than or equal to 0. Then a is bigger than or equal to 0 using that infimum. Still reaching lim inf is equal to 0. So in that case, right? So in that case, combined, like I said, as long as I can show lim inf is equal to lim sup, because remember, this is the infimum of all the limit points. That's the supremum of all the limit points. Right? If they equal to each other, so meaning there's only one limit point. Right? If any subsequence is convergent, right, you take all the possible convergent subsequences, they all converge to a single same limit point, which means the original sequence also converges to that same limit point, that is 0. So yes.